All right, today we're going to dive into what is honestly one of the most important moments in AI history. We're talking about that massive shift in computer vision, how we went from this world of, handcrafting every single role to the deep learning breakthrough that finally taught computers how to actually see. So you got to ask, right? Before all this deep learning stuff, how in the world did we teach a computer to see? Like, how do you explain what a cat is or a car? Turns out it was a really manual and honestly super fragile process. Yeah, this was what we call the hand-engineered era, a time when for every single visual task, you needed a human expert to sit down and write a very specific, rigid set of rules. There wasn't any learning from data like we think of it now. It was all just explicit instructions, and man, were they brittle. Okay, to really get a feel for this, let's look at a real-world problem from back then. Just trying to tell different kinds of rice apart. Basmati from jasmine just by looking at a picture? Sounds pretty simple, doesn't it? Huh. Well, the logic behind it was anything but. The whole process was this delicate house of cards. First, you'd have to write code to basically cut out the background, just isolating the grains based on pixel brightness. Then, you'd apply these special handmade filters to find the edges of each grain. After that, you'd use a math formula, a least squares algorithm, to try and fit a perfect ellipse around each one to measure it. And what if two grains were touching? Oh, well, that needed even more custom code just to handle that one specific problem. So here's the kicker, right? Every single one of those steps was defined by a person. And this approach was just impossible to scale. It couldn't generalize at all. A model you painstakingly built for rice grain was completely useless for identifying, well, anything else. The whole system was just fundamentally brittle. And then, boom, everything changed. The year is 2012, and the annual AlexNet competition, think of it like the Olympics for computer vision, was about to see something so crazy it would completely rewrite the rules of the entire field. And this chart, this is the proof. Just look at the error rates from the early years of the competition. They're all kind of clustered together up there. Now look at that massive nosedive in 2012. That single point just plummeting way below everyone else. That is the arrival of a deep learning model called AlexNet. Let's put some actual numbers on this because it's wild. The winner from the year before, 2011, had what's called a top 5 error rate of 26.2%. That means for more than a quarter of the pictures, the right answer wasn't even in its top 5 guesses. AlexNet came in with an error rate of 15.3%. That's a drop of over 10 percentage points. This wasn't just a small step forward, it was a whole new ballgame. So, the big question is how? How did AlexNet do it? What were the secret ingredients that let it just completely crush the competition? Let's pop the hood and take a look at the anatomy of this revolution. Okay, first up, AlexNet totally changed how the artificial neurons actually work. See, older models used these saturating functions, like sigmoid or tan. You can see on the graph how they kind of flatten out at the ends. The problem is, when they flatten out, the signal for learning, the gradient, it just vanishes, shrinks to almost nothing. This is the classic vanishing gradient problem, and it makes training painfully slow. AlexNet switched to a much simpler non-saturating function called a rectified linear unit, or ReLU. And that one simple change solved the problem. And the impact of this one change, it was insane. On a standard data set, a network using these ReLUs hit its goal error rate a full 6 times faster than a similar network using the old-school tanh neurons. That kind of speed up was absolutely critical for training a really deep model on a massive data set like ImageNet. All right, next up was a really cool technique called local response normalization. It was actually inspired by how real neurons work in the brain, a process called lateral inhibition. Basically, when one neuron gets really excited, it kind of tells its neighbors to quiet down. In the model, this created a sort of competition between the neuron outputs. It forced the model to focus only on the most important signals and learn features that were much more distinct in general. And this just goes to show you how every single little tweak mattered. Just by adding this one normalization layer, AlexNet dropped its top 5 error rate by 1.2% and its top 1 error by 1.4%. I know that doesn't sound like a lot, but when you're competing at this level, those are huge gains that all add up. AlexNet also tweaked a process called pooling. So traditionally, models would look at features from separate, non-overlapping little boxes on an image. AlexNet did something different. It used overlapping windows instead. Think of it like a smoother, more redundant summary of all the features. This made the model way more robust and less likely to get thrown off by the exact location of an object. In other words, it helped reduce overfitting. Now, the improvement here was smaller, for sure, but you could still measure it, a 0.3% drop in top 5 error. It really drives home the point that when you're trying to do something revolutionary, every single architectural choice, every tiny fraction of a percent adds up to make a massive difference in the end. And finally, let's be clear, none of this magic would have happened without a really smart data pipeline. All the images were first shrunk down to a fixed 256 by 256 size. Then, to normalize them, they calculated the average pixel value across the entire training set and subtracted it from every single image. But the real key was aggressive data augmentation. They would take random 224 by 224 patches from the images and their mirror images and even mess with the RGB color channels. This basically blew up the size of the training data and was absolutely essential for stopping the model from just memorizing the training set. Okay, so let's zoom out from all the technical stuff for a second and look at the big picture. AlexNet didn't just win a contest. It slammed the door on one era and kicked open the door to a brand new one. It was the moment we went from brittle, human-made rules to the incredible power of machine-learned representations. And this is the real takeaway. Researchers no longer had to be these hyper-specialized experts, handcrafting features for every single new problem. The new way forward was to build these big general-purpose networks and just let them learn the important features themselves, directly from tons and tons of data. But you know what? The story doesn't stop there. AlexNet and the rise of the CNNs, that was the foundation. But another game-changing idea was lurking just around the corner. An idea that would lead us straight to the transformer models that are running so much of the AI world today. This timeline really lays out how fast things moved after that. So in 2012, AlexNet proves that deep CNNs are the way to go for vision. But the field kept sprinting. Just 2 years later, in 2014, this new idea pops up, the attention mechanism. It let models dynamically focus on the most important parts of whatever they were looking at. And by 2017, that little seed of an idea had exploded into the revolutionary transformer architecture, announced in that legendary paper, Attention is All You Need. So think of it like this. If the whole CNN revolution gave AI a powerful set of eyes to see the world, well, the invention of attention was about to give it a whole new way to reason about what it was seeing. This set the stage for everything that came next, vision transformers, the multimodal AI we see today. And it really makes you wonder, what's the next great leap going to be?